Let's calculate the percentage dissociation of 0.65 molar of hydrogen cyanide. So we're given the pKa, which is 9.21, so we have to find the Ka. So to find the Ka, we have to use this equation. So pKa is equal to negative log of Ka. So we are looking for Ka. So Ka is equal to 10 to the power of negative pKa, which is equal to 10 to the power of negative 9.21. And Ka is now equal to 6.166. Multiply that by 10 to the power of negative 10. So now that we have the Ka, we have to write the dissociation reaction for hydrogen cyanide. So we have hydrogen cyanide aqueous plus H2O liquid reversible reaction. So hydrogen cyanide is going to donate a proton. It's going to give away this hydrogen to H2O. So H2O is going to have 3 hydrogens now. So we have H3O plus aqueous plus, now hydrogen cyanide will be left with no hydrogen. So it's going to be cyanide minus aqueous. Now we have to write the Ka expression for this reaction. So the Ka expression is going to be that value. So we have 6.166 multiplied by 10 to the power of negative 10 is equal to the product of the concentration of hydronium ion and that ion over there. So we have H3O plus and the concentration of Cn, and then divide that by the concentration of hydrogen cyanide. So we have HCN. And from now we have to draw the reaction table. Now let's plug in the values that we have. So the initial concentration for hydrogen cyanide is 0.65. Water has been excluded. So let me use another color. So we have 0.65, water being excluded, and we have 0, 0. And the change is going to be minus x excluded plus x plus x. So the equilibrium concentrations 0.65 minus x, and here we're going to have x and x. So now we have to find the value of x. So we're going to use the Ka expression to find the value of x. So we have that value, which is 6.166 multiply that by 10 to the power of negative 10 is equal to the concentration of hydronium ion, which is x, and the concentration of cyanide ion, which is x. So we have x and x, divided that by the concentration, the equilibrium concentration for hydrogen cyanide, which is 0.65 minus x. So from here we're going to multiply both sides by 0.65 minus x, and you should get 4.01 multiplied by 10 to the power of negative 10 minus 6.166 multiplied by 10 to the power of negative 10x, and that is equal to x squared. So we can take everything to the other side. So we have x squared plus 6.166, multiply that by 10 to the power of negative 10x minus 4.01 multiplied by 10 to the power of negative 10. So you can plug that into a calculator and solve for the value of x. And x is equal to 2 times 10 to the power of negative 5. And this, since x represents the equilibrium concentration, so this is concentration. So now let's find the percentage dissociation. So we can assume that the equilibrium concentration of hydrogen cyanide is equal to the value of x. So we can assume, because it's a weak acid and it does not dissociate completely, so we can say 0.65 minus x is almost equal to the value of x. Okay, so if we do not assume that the equilibrium concentration of hydrogen cyanide is closer to x, it will give us a solution that the percentage dissociation of hydrogen cyanide has completely dissociated, and which is not correct, because hydrogen cyanide is a weak acid and it does not dissociate completely. So let me demonstrate here. So we have that concentration. So we're going to find the percentage dissociation if we did not assume that condition. So the percentage dissociation is equal to 0.65 minus x divided by the initial concentration of hydrogen cyanide, which is 0.65. Multiply that by 100. So we have 0.65 minus x, which is that concentration over there, to multiply by 10 to the power of negative 5 divided by 0.65, multiply that by 100, and we should get a value of 99.99692308%. This just shows us hydrogen cyanide has dissociated completely, which is not correct, because a weak acid does not dissociate completely. So that is why we assume that condition over there. So we have that. So the percentage dissociation is equal to that value x, which is 2 multiplied by 10 to the power of negative 5 divided by the initial concentration, which is 0.65, and multiply that by 100. You should get 0.0031%, which is most likely to be true, because weak acids do not dissociate completely. And this will be your final answer.